Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you enjoyed the podcast, show your support with a like, a follow, or a comment.
Thank you so much for having me. I'm really excited to dig into this today.
Yeah, we are thrilled to have you here. So, for the listener, imagine pressing the gas pedals in your car, right? But instead of just moving the vehicle, you also have to physically drag the entire atmosphere around you.
Oh man, that would be rough.
Right.
Hmm.
Suddenly your 2-ton car feels like it weighs 50 tons. The steering becomes incredibly sluggish, the brakes barely work, and every time you turn the wheel, an invisible hand violently shoves the back of the car in the opposite direction.
Which sounds like just a catastrophic mechanical failure. But what you are describing is actually the fundamental everyday reality of designing machines that operate in dense fluids.
It's crazy to think about.
It really is. I mean, we have a tendency in engineering to look at a blueprint, point to a steel beam, calculate its yield strength, and, treat it as a static, isolated object in a vacuum.
And I guess that works perfectly fine if you are building like a bridge in a relatively calm environment. Civil engineers get to enjoy that concrete precision.
Exactly. They have it easy in that regard.
But today, our mission for you, the listener, is to take you through what is essentially a masterclass on the dynamic, highly coupled world of fluid mechanics and structural design. We are going straight into a deep dive on this.
Yes, we're going to bridge that massive gap between abstract fluid theories and the really gritty realities of building things like submarines, nuclear reactors, and even refrigeration systems.
So by the time we wrap up this deep dive, you should understand not just how objects move through fluids, but exactly why they behave the way they do. And that's based on, geometry, mass, and elemental thermophysical properties.
Right, because we need to shift the paradigm. You have to stop looking at the machine as an isolated entity and start viewing it as, well, half of a coupled system.
Okay, so the fluid it sits in is the other half.
Precisely. Whether that is ocean water, highly pressurized steam, or a complex refrigerant. When you immerse a structure in a fluid, the structure fundamentally loses its individual identity.
Wait, loses its identity. That's a strong way to put it.
It is, but it's true. It adopts a completely new dynamic identity that's dictated by the unseen forces of the medium surrounding it.
Wow. Okay, let's start with the most pervasive of those unseen forces. The sources we're examining describe a phenomenon that happens the exact moment you place a structure into a fluid.
Right, the vibrational characteristics are instantly altered.
Yeah, even if the fluid is completely still. I think the literature calls it a quiescent fluid. The natural frequencies of the structure decrease and the damping increases.
Exactly. But the real mechanism we need to unpack today is what happens when that object accelerates. The texts refer to this as added mass or virtual mass.
Okay, so what is physically occurring in the fluid to cause this added mass? Like, my car doesn't literally gain mass on the highway.
Right, and that's why the term added mass can be slightly misleading. The object itself isn't, gaining physical atoms of steel.
That would defy physics.
It really would. What is happening is a forced reallocation of the surrounding environment. So to move an object through a fluid, you can't just magically occupy a new space.
You have to push the stuff out of the way.
Exactly. You must evict the fluid that currently occupies that space. As the front of the object pushes forward, it accelerates a massive envelope of fluid out of its path.
And I assume something has to fill the space it leaves behind.
Right. Simultaneously, fluid must violently rush in behind the object to fill the void left in its wake, and all of that fluid possesses its own mass and its own inertia.
So it resists being accelerated.
You hit the nail on the head.
Okay, so the energy you're expending isn't just to overcome the inertia of the steel or titanium that you physically built.
No, not at all. You are paying a heavy energy tax to physically accelerate the fluid around it.
That makes so much sense. So how do we quantify that tax?
Well, the mathematics of this energy tax are actually quite beautiful, particularly when we look at ideal, incompressible, and irrotational fluids.
Okay, hit me with the math.
In fluid dynamics, we define this flow using a velocity vector denoted as v. The math states that this velocity vector is equal to the gradient of the potential function. So v equals nabla phi.
Okay, let's translate that math for the listener, because just hearing v equals nabla phi, or the gradient of a potential function, doesn't give us physical picture.
Fair enough.
The gradient essentially represents the rate of change in all three spatial directions. right? Like up, down, left, right, forward, backward.
Yes, exactly. That spatial mapping is incredibly critical because it leads us directly into Laplace's equation.
Which is what?
The requirement is that the Laplacian of this potential function must equal 0. Mathematically, that's nabla squared phi equals 0.
Okay, and physically, Laplace's equation enforcing that strict zero value is essentially a strict rule of real estate in the fluid, right?
That's a great way to put it. A rule of real estate.
Yeah, like it means the fluid is incompressible. Water cannot be magically squished into a smaller volume, and it can't spontaneously disappear.
Precisely. If a submarine pushes into a new cubic meter of space, an exact equal cubic meter of water must get out of its way. The math is just, meticulously balancing the volumetric checkbook.
I love that, balancing the checkbook.
And by balancing that checkbook, we can derive the exact force the fluid exerts back onto the accelerating body.
Okay, what does that equation look like?
The equation reveals that the fluid force, F, is equal to the negative of this virtual mass term, little m, multiplied by the partial derivative of the flow velocity, u, with respect to time, t.
Okay, wait, let me process that. The derivative of velocity with respect to time is literally just acceleration.
Exactly.
So strip down, this F equals negative m times partial u over partial t is literally just Newton's second law. Force equals mass times acceleration.
It is. It's that fundamental.
But the mass in this specific equation is not the physical weight of the object. It is this dynamic, invisible envelope of fluid.
You've got it perfectly.
But this brings up a really critical question of scale for the listener.
Okay, what's that?
If every object moving through a fluid experiences added mass, why don't automotive engineers constantly worry about the added mass of the air when they're designing a car?
That is a fantastic point. Automotive engineers can safely ignore it because of the density ratio rule.
Density ratio rule.
Yeah, so added mass only becomes a significant design-altering fraction of the total dynamic mass when the density of the fluid is comparable to the density of the structure.
Oh, I see. And air is incredibly sparse compared to the dense steel and aluminum of a car.
Exactly. The mass of the air being shoved out of the way is literally just a rounding error compared to a 2-ton chassis.
But the ocean is a completely different story.
Oh, a vastly different story. Seawater is roughly 800 times denser than air as sea level.
Wow. 800 times.
Yeah. So consider a massive military submarine. When the captain orders a hard acceleration or a rapid dive, the propellers aren't just fighting the inertia of the submarine's titanium hull.
Right.
They are fighting the inertia of thousands of tons of heavy water that must be dragged along with the vessel.
That's terrifying from a control perspective.
It really is. If a control systems engineer programmed the diving planes and rudders based solely on the dry weight of the submarine, the vessel would dangerously overshoot every single maneuver.
Because the momentum of that virtual water envelope would just keep pushing the submarine long after the physical engines tried to stop it.
Precisely.
This means a designer cannot just, weigh a part on a scale in a laboratory and call it a day. You have to calculate its dynamic wet weight.
Yes, it's wet weight. That's the crucial metric.
And if the submarine is dragging this massive virtual envelope, I have to assume the specific shape of the hull dictates exactly how much water gets trapped in that envelope.
Oh, geometry absolutely dictates the physics here.
Because a blunt, brick-like object is going to drag a completely different volume of water than a sleek teardrop shape.
Exactly. The specific contours of the object determine the flow potential, which in turn defines the exact magnitude of the added mass.
So what kind of numbers are we talking about? Does the literature give us examples?
It does. The sources give us some pristine geometric examples. Let's start with 2 dimensions. If you take a perfectly infinitely long cylinder of a certain radius, let's call it A.
Okay, an infinitely long cylinder, radius A.
The mathematical derivation shows that the added mass per unit length is equal to the fluid density, rho multiplied by pi multiplied by A squared.
Wait, hold on. Rho times pi times A squared?
Yes.
That is fascinating because pi times the radius squared gives you the cross-sectional area.
Right.
And multiplying that area by the density, rho, gives you the exact mass of the fluid that the cylinder displaced.
You see the elegance of it?
Yeah. For a perfect cylinder, the added mass is an elegant 1-to-1 ratio with the displaced fluid mass. It's perfectly equal.
It is a rare moment of mathematical symmetry in engineering. But as you know, mechanical design rarely relies on infinitely long, perfectly smooth cylinders.
Right, we have brackets and fins and all sorts of complex shapes.
And when you introduce sharp geometries, the added mass penalty absolutely skyrockets.
Really, how much worse does it get?
Well, if you take a square cross-section that shares the exact same primary dimensions as that cylinder, the added mass factor jumps significantly, up to 1.51 times the displaced volume.
Whoa, 1.51. That jump makes physical sense, though, when you think about the boundary of the shape.
How so? Walk the listener through your thought process.
Well, a smooth cylinder allows the fluid to glide around its curvature, right?
Yeah.
The water parts at the front and smoothly rejoins at the back.
Right.
But a square has harsh 90-degree corners. Those corners have to disrupt the flow, creating zones of stagnation where extra dead fluid gets trapped and dragged along.
Exactly. You aren't just moving the square, you are moving the square plus roughly 4 triangular wedges of trapped water on those flat faces.
That's wild. What about in 3 dimensions?
Moving into 3 dimensions, the geometry continues to dictate the terms. A perfect sphere has an added mass equal to exactly half of its displaced fluid mass, or 2/3 rho times pi times a cubed.
Okay, so half for a sphere.
But a solid cube drops to a coefficient of roughly 0.68 times its displaced mass, or 0.7 times rho times a cubed.
Wait, so a sphere is 0.5, but a cube is 0.68.
Yes, the flow field around a 3-dimensional corner is vastly different from a 2-dimensional corner.
Okay, but discussing these ideal flow fields brings us to one of the most famous and historically frustrating concepts in fluid mechanics.
Yes. You're talking about the D'Alembert paradox.
Yes. For the listener, this is a concept that historically caused a massive rift between theoretical mathematicians and practical engineers.
It really did. They were practically at each other's throats.
The paradox, formulated by Jean-Laurent D'Alembert in the 18th century, states that for an ideal inviscid fluid, meaning a perfect fluid with 0 viscosity and 0 internal friction,
Right, a mathematically perfect fluid.
the drag force on a body moving at a steady, constant velocity is absolutely 0.
0 drag.
Which sounds completely wrong.
Well, from a purely mathematical standpoint, in an inviscid flow, it is completely sound. As the object pushes through this frictionless fluid, the fluid splits at the front, creating a zone of high pressure.
Okay.
It flows around the body and perfectly symmetrically reconverges at the rear, creating an equal zone of high pressure pushing forward.
Oh, I see. The pressure at the front cancels the pressure at the back.
Precisely. The net drag force is mathematically 0. The force of added mass we've been talking about only exists when the object accelerates or decelerates, which unbalances that pressure field.
But the practical engineers building ships and aqueducts in the 1700s looked at these mathematicians and thought they were totally insane.
Of course they did. Anyone who has ever rowed a boat knows that water exerts a continuous drag force even when you are moving at a constant speed.
Right. The disconnect existed for over a century until we truly understood boundary layers and viscous friction.
Yes, real fluids have friction.
But the paradox remains a vital teaching tool, right? Because it isolates the purely inertial component of the fluid from the friction component.
Exactly. It forces us to separate acceleration forces from velocity forces. We can visualize this separation through a really simple physical analogy.
Okay, let's use the analogy of standing chest deep in a swimming pool, holding a flat, wide wooden paddle.
Perfect.
If you hold the paddle flat against the water and try to rapidly wave it back and forth, accelerating and decelerating it rapidly, it feels impossibly heavy.
Right. It takes immense effort.
And that massive resistance is the added mass fighting your acceleration.
Yes.
But if you turn that exact same paddle sideways, edge first, and thrust it forward at a constant speed, it slices right through the water with minimal effort. The difference is staggering.
It's night and day. And that paddle analogy reveals another layer of complexity that goes beyond simple scalar mathematics.
What do you mean by scalar mathematics?
I mean, just assigning a single number to the added mass. The resistance you feel depends entirely on the orientation of the object relative to the direction of acceleration.
Right, flat versus edge first.
Exactly. So in engineering, we cannot just assign a single number to the added mass of a complex shape. We must represent it using an added mass tensor.
A tensor, okay. For the listener, a tensor in this context is essentially a matrix, right? Like a spreadsheet of cross-coupling coefficients.
That's a great visualization.
It maps out how accelerating in one specific direction generates forces in all the other spatial directions.
Yes. The mathematics denote this as a matrix where the coefficient m subscript ij dictates the force.
M subscript ij.
In many ideal cases, this matrix is symmetric, meaning the coefficient m subscript ij equals m subscript ji. The reciprocal coupling is balanced.
Okay, but what is the critical takeaway for a mechanical designer here?
The takeaway is that for highly asymmetrical structures, accelerating straight forward can induce massive, unexpected forces in entirely different directions.
Wait, let me make sure I'm visualizing this correctly. If I design an asymmetrical object, and I apply a thrust vector perfectly straight along the x-axis,
Right?
the fluid might actively shove the object sideways along the y-axis.
It will shove it sideways, and it will very likely induce a rotational moment as well. It will try to spin the object.
That is insane.
Let's consider the design of an underwater, remotely operated vehicle, an ROV, like the ones used for deep-sea pipeline inspection.
Okay, so like a little submarine drone.
Exactly. These vehicles are often modular. An engineer might bolt a heavy, bulky camera payload onto the left side of the vehicle and then add a smooth buoyancy block to the right side to keep the static weight balanced in the water.
So it floats perfectly level when it is sitting still.
Yes. But dynamically, the shape is completely asymmetrical. The bulky camera has a drastically different added mass tensor than the smooth buoyancy block.
Oh, I see where this is going.
The moment the ROV fires its rear thrusters to accelerate straight forward, the fluid will resist the bulky camera much harder than the smooth right side. The fluid itself generates a massive twisting force.
So if the control algorithms do not actively calculate and counteract that specific added mass tensor, the drone will just immediately spiral out of control the second it tries to move forward.
It would just do donuts in the water.
So the fluid isn't just a passive background environment. It acts as an active mechanical linkage that manipulates the object based on its geometry.
Precisely. It is an active participant.
And this entire discussion so far has only been about a single isolated object moving through a fluid. The reality of mechanical design is rarely that lonely.
Very true.
We need to transition to what happens when you have multiple structures in close proximity immersed in the same dense medium.
Yes. This brings us to the concept of inertial coupling.
Inertial coupling.
When two or more objects are placed close together in a fluid, the added mass is no longer just a localized property of one isolated shape.
Because the flows interfere.
Exactly. The flow field of the first object intersects with the flow field of the second object. The added mass becomes a highly sensitive function of the physical spacing between them.
The classic configuration analyzed in the text we have is a cylindrical rod centered perfectly inside a larger, fluid-filled outer cylinder.
Essentially a pipe within a pipe.
Right, with the annular gap between them completely filled with liquid.
Now, if you perform this experiment in a vacuum chamber with absolutely no fluid, shaking the inner rod does absolutely nothing to the outer pipe.
Right, because they are mechanically isolated. There's just empty space between them.
Exactly. But the exact moment you fill that gap with a dense fluid, the fluid transforms into an invisible, highly rigid mechanical spring.
Because of the incompressibility rule we talked about earlier?
Precisely. You remember the real estate rule.
Yeah. If the inner rod accelerates toward the outer wall, the fluid caught between them must be violently displaced.
And that fluid is forced directly against the outer cylinder, transferring all of that kinetic energy. The mathematical equations of motion become fully coupled.
So the physical force exerted on the outer pipe is directly dictated by the acceleration of the inner rod, communicating entirely through that fluid gap.
Yes. The sources indicate that this coupling effect increases dramatically as the fluid gets denser and as the gap gets tighter.
So if you have a massive inner spiel rod and only, say, a 1 millimeter gap of water separating it from the outer shell,
violently shaking the inner rod is going to instantly jerk the outer shell as if they were physically bolted together.
the fluid just locks them together.
It does, and while a pipe in a pipe is a neat laboratory example, the industrial applications of this phenomenon are monumental.
Let's give the listener a real-world example.
Consider the heart of a pressurized water nuclear reactor or a massive petrochemical refinery. The primary method of transferring energy in these facilities is through shell and tube heat exchangers.
Right, a commercial nuclear steam generator isn't just one pipe. It is an array of thousands of U-shaped metal tubes,
Thousands of them.
packed incredibly tightly inside a massive steel vessel, with thousands of gallons of high-pressure water rushing past them every minute.
Now, if an engineer looks at a single tube in isolation, they might calculate its natural resonant frequency and determine that it is plenty stiff enough to withstand the flow of the water.
Sure.
Furthermore, if the tubes are spaced widely apart, The literature generally cites a distance of more than 2 diameters from center to center. The fluid effects remain mostly localized.
So the fluid just adds a bit of static virtual mass to each independent tube. No big deal.
No big deal, but what is the entire goal of a heat exchanger?
Thermal efficiency.
Right. And which means maximizing surface area. So engineers pack those thousands of tubes as close together as physically possible without them actually touching.
And by packing them tightly, they invite catastrophic inertial coupling.
They absolutely do. The tiny fluid gaps between the tubes act as a massive network of invisible springs tying the entire array together.
So when one tube vibrates slightly due to the water flowing past it, it pushes the fluid into the adjacent tube.
Yes, which pushes the fluid into the next tube and the next.
The fluid ties them into a single, massive, vibrating ecosystem.
And this coupling drastically lowers the natural frequencies of the system as a whole. It creates highly complex group vibration modes.
Wait, group vibration modes?
The tubes no longer vibrate independently, they lock into synchronized patterns. If the velocity of the fluid flowing through the shell happens to align with one of these new, lower group frequencies, the system hits resonance.
Oh no.
Oh yes. The entire array of thousands of tubes will begin to oscillate in perfect destructive harmony. The fluid amplifies the energy until the tubes violently clash into each other,
Rupturing the metal and causing a catastrophic failure of the heat exchanger.
a multi-million-dollar failure just because they didn't account for the fluid acting as a spring.
That is wild. And it isn't just the physical tubes violently hitting each other that the designer has to worry about, right?
No, it does not.
Because all that chaotic, coupled movement, the fluid rushing and separating around the tightly packed geometries, generates severe pressure fluctuations in the fluid itself.
That's right.
And what is a fluctuating pressure wave traveling through a fluid medium? It is sound.
It is sound, which brings us perfectly to the acoustics of fluid flow.
Vibration and acoustics are essentially two sides of the same thermodynamic coin, right? Sound is, at its core, mechanical vibration propagating through a fluid.
Absolutely. What the study of fluid mechanics reveals is a stunning universality in how sound waves are generated by turbulent flow, completely regardless of the scale of the machine.
For whether it's tiny or huge, the physics are the same.
Exactly. The moment a fluid stops flowing perfectly smoothly along a surface, the moment it separates, tumbles, and forms swirling vortices, it begins exerting random, chaotic pressure pulses on the structure.
And those pulses don't just shake the metal, they radiate outward as acoustic energy.
The underlying physics of this aerodynamic noise generation are governed by the exact same mathematical principles, whether you are looking at a microscopic system or an aerospace leviathan.
The contrast the sources use to illustrate this is incredible. Picture a tiny half-inch pressure relief valve on a factory compressed airline.
Okay.
When the pressure spikes and that valve pops open, a high-velocity jet of gas screams out into the room. It produces a piercing, incredibly loud hiss.
We've all heard that noise in a factory. Now, compare that tiny valve to the exhaust nozzle of a commercial turbofan jet engine producing 100,000 pounds of thrust at takeoff.
The physical scale difference is astronomical.
The temperatures are vastly different. The thrust is vastly different. Yet, the acoustical characteristics of that screaming pressure relief valve share the exact same fundamental noise-generating mechanisms as the massive jet engine.
So you're saying the turbulent shear lay at the boundary where
Yeah.
the fast-moving air rips against the slow-moving ambient air coming off that tiny little valve?
Yeah.
It follows the exact same decay rate and acoustic profile as the exhaust of the jet engine.
It genuinely does. The mathematics governing the turbulent eddies, the quadrupole sound sources defined by Sir James Lighthill's acoustic analogy, and the conversion of kinetic flow energy into acoustic pressure waves are totally identical.
Lighthill's acoustic analogy.
Yes, it is a universal scaling law.
The literature also draws a direct line between the small plastic cooling fan inside a desktop computer or a household air conditioner and the massive multi-stage axial compressors inside a gas turbine.
It's the same mechanism. The flow separation that happens over the blade of a 2-inch plastic computer fan generates noise using the exact same vortex shedding mechanisms as a solid titanium turbine blade.
That's amazing. Even the aerodynamic noise you hear inside your car
Yeah.
on the highway, the wind rushing past the sleek side mirror. That is governed by the same flow separation physics that dictate the aerodynamic noise of a commercial airplane wing slicing through the atmosphere.
It is. And for a mechanical engineer, this universality is a massive, massive advantage.
Why is that?
Because it means you don't have to build a full-scale jet airliner to understand aeroacoustics.
Oh, I see.
If you spend your time meticulously solving an annoying whistling problem caused by vortex shedding on a small automobile side mirror, you are essentially mastering the exact same physical laws that quiet down the landing gear of a Boeing 777.
You are interacting with universal principles.
Exactly. The acoustic power generated by turbulence scales predictably with flow velocity, fluid density, and a characteristic length dimension. Understand the physics of the small system, and you hold the key to predicting the behavior of the giant system.
Okay, so to survive these massive fluid forces, the added mass, the inertial coupling, the violent acoustic vibrations we just talked about, the engineer must select the right materials.
You can't just build a submarine out of tinfoil.
No, you definitely cannot. Which leads us into analyzing the material palette. We need to look at the raw thermophysical data of structural solids across extreme temperature ranges.
Material selection in dynamic fluid environments is a really complex balancing act. You are not simply looking at a material's cost or its static yield strength.
What else are you looking at?
You must evaluate its density, its heat capacity, and its thermal conductivity. Crucially, you must understand how those specific properties behave when the system experiences massive thermal loads.
So temperature changes everything.
It really does.
Yeah.
The extreme ends of the periodic table provide the best perspective on this. Let's examine tungsten.
Ah, tungsten. Tungsten is the absolute heavyweight champion of structural metals.
It really is.
The sources list its density at over 19,000 kilograms per cubic meter. It is astonishingly dense and heavy.
But its density is only part of the story. What makes tungsten an absolute engineering marvel is its extreme thermophysical stability.
Stability, what does that look like?
When you expose tungsten to immense thermal energy, literally blasting it with thousands of degrees of heat, its atomic lattice remains remarkably rigid. It retains a highly stable heat capacity and thermal conductivity profile. It does not flinch under thermal duress, providing massive, unwavering structural inertia.
Let's contrast that dense stability with the featherweight of the material world. Lithium. The
Lithium.
elemental density of lithium is listed at only 534 kilograms per cubic meter.
That is incredibly low.
It is nearly 40 times lighter than tungsten. It is so light that solid lithium metal will literally float on water.
But while it lacks density, its thermal behavior is incredibly aggressive. The heat capacity of a material, which is denoted as C sub P, measures how much thermal energy is required to raise its temperature.
Right.
As lithium heats up, its heat capacity C sub P absolutely skyrockets, reaching massive levels over 5,200 joules per kilogram Kelvin.
To put that into physical terms for the listener, how does the atomic structure of lithium actually absorb all that heat compared to tungsten?
Well, heat at the macroscopic level is simply atomic vibration at the microscopic level. We track this vibrational energy using quasi-particles called phonons.
Phonons, right.
Tungsten has a very dense, tightly bound crystal lattice. It takes a massive amount of energy to get those heavy tungsten atoms to vibrate significantly.
So it resists heating up.
Exactly. Lithium, however, has a much looser, lighter atomic structure. When you apply heat, the lithium atoms vibrate intensely and freely. The material acts as an absolute thermal sponge, soaking up massive amounts of vibrational energy.
And looking at the other metals in the sources, we see elements like silver and platinum occupying different specialist roles.
Yes. Let's look at silver.
Silver boasts an astonishing thermal conductivity, represented by the Greek letter lambda, pushing over 400 watts per meter Kelvin.
It doesn't just absorb heat, it rapidly shuttles it away across its crystal lattice. It's a highway for heat.
And platinum, conversely, remains dense, heavy, and structurally uncompromising, behaving much more like tungsten.
Every single material offers a distinct physical trade-off.
So let me play devil's advocate here to tie these concepts together for the listener.
Okay, go for it.
If lithium is so incredibly light, and it has the capacity to absorb massive amounts of thermal energy, why don't we see it used more in heavy industry?
Why not use it everywhere?
Yeah. Why aren't we building the internal structures of submarines or the cooling fins of marine heat exchangers out of lithium alloys to save weight?
That question requires us to bridge our knowledge of materials back to our very first discussion today. The density ratio rule of added mass.
Right, the ratio of the structure's mass to the fluid's mass.
Imagine you build a complex, highly engineered internal structure out of a super lightweight lithium alloy.
Okay, I'm imagining it.
You then immerse that structure in a dense fluid like pressurized water or a heavy industrial coolant. Because the solid structure is so exceptionally light, the virtual mass of the dense fluid surrounding it completely dwarfs the physical mass of the lithium.
Oh, the fluid becomes the dominant inertial force in the system.
Exactly. If there's any turbulence in the flow, any vortex shedding or acoustic pressure waves, the heavy fluid will violently throw that lightweight structure around.
Because it has no mass to resist it.
Right. The inertial coupling between the lightweight components will be catastrophic. The solid structure simply lacks the inherent mass to anchor itself against the invisible springs and forcing functions of the fluid.
It would be like trying to hold a styrofoam cup completely still underwater while a wave pool generator is running. The cup just doesn't have the mass to fight the water.
That is a perfect physical visualization. Sometimes an engineer absolutely relies on the massive, uncompromising density of tungsten, nickel, or platinum.
You don't just need those metals for their high-yield strength. You need them for their dynamic inertia.
Yes. You need a massive physical anchor to resist the powerful coupled fluid dynamics trying to tear the entire system apart.
That is a profound paradigm shift for mechanical design.
Mm.
You aren't just choosing a metal because it is strong enough to hold a static load. You are choosing it for its dynamic mass ratio against the specific fluid it will operate in.
It is a totally different way of thinking. Which brings us to the final and perhaps most complex piece of the engineering puzzle today.
Let's hear it.
The structures do not act alone, and the fluids rushing through them are rarely just simple water.
Right. In many industrial applications, particularly power generation and HVAC, the fluids pumping through the system are highly complex chemical refrigerants.
Yes. Up until now, we have mostly discussed fluids as if they were consistent, well-behaved mediums. But when we analyze industrial refrigerants like R12, R134A, or R22, their thermophysical properties are anything but consistent.
The data tables provided in the sources for these refrigerants are vast, and they highlight a critical reality. These fluids change radically with temperature.
They do. And when they undergo a phase shift, meaning boiling from a liquid into a vapor, the fundamental rules of physics governing their behavior practically invert.
Invert, like they go backward.
Pretty much. Let's examine viscosity, denoted by the Greek letter eta. Viscosity is the measure of a fluid's internal friction, its resistance to flow.
So it dictates how hard a pump has to work to push the fluid through a pipe.
Exactly. Now, if you take a liquid refrigerant and apply heat to it, the data shows that its viscosity drastically drops. It becomes thinner, much more runny.
At a molecular level, the liquid state is held together by intermolecular bonds, right?
Yes. When you add thermal energy, you are providing the molecules with enough kinetic energy to begin breaking those weak bonds.
And as the bonds break, the molecules can slide past one another with much less resistance.
So the internal friction decreases.
That perfectly aligns with our everyday experience. If you put cold, thick honey in the microwave and heat it up, it becomes a thin liquid that pours easily.
Exactly. But the data tables reveal a wild contradiction when we look at the vapor state.
Right.
If you take that exact same refrigerant, completely vaporize it into a gas, and then continue to heat it up, its viscosity actually increases.
Wait, really?
Yes. The gas gets thicker, it becomes more resistant to flow.
How does heating a gas create more friction? That feels completely backwards.
It is a beautiful demonstration of the kinetic theory of gases. In a liquid, the molecules are packed tightly together, fighting intermolecular bonds. But in a gas, the molecules are already spread far apart. Those bonds are completely broken.
So adding heat can't break bonds that don't exist anymore.
Exactly. Instead, the thermal energy translates directly into kinetic velocity. The gas molecules begin zipping around the space at much higher speeds.
Okay, I follow that.
Because they are moving so much faster, they collide with one another much more frequently.
Let's use an analogy here for the listener. Imagine trying to walk down a long enclosed hallway filled with people.
A crowded hallway, okay?
If everyone in the hallway is standing perfectly still,
Huh.
which represents a cold gas with low kinetic energy, you can easily weave your way through the crowd. The resistance is low.
Right.
But if you add heat, if suddenly everyone in that hallway starts sprinting back and forth in a frantic panic, trying to walk through that chaotic, high-energy crowd is going to result in constant violent collisions.
You're going to get bumped around constantly.
The friction of the crowd is massively higher.
That hallway analogy perfectly captures the macroscopic effect of microscopic momentum transfer. The increased rate of high-speed molecular collisions across the different layers of the flowing gas creates a severe drag force.
So heating a liquid reduces friction by breaking bonds, but heating a gas increases friction by increasing the collision rate.
You summarize it perfectly.
That inversion fundamentally alters how a mechanical compressor operates depending on the exact temperature of the gas it is pushing.
It absolutely does. But viscosity isn't the only property that drastically shifts. We also need to look at the speed of sound within the refrigerant, represented by the variable W.
Okay, the speed of sound, W. The speed of sound is not a universal constant, right?
No, it is a mechanical property of the specific medium it travels through. It is dictated by the fluid's density and its bulk modulus, which is essentially a measure of the fluid's stiffness or compressibility.
So in the dense liquid state of these refrigerants, the speed of sound is incredibly fast. The data says often well over 1,000 meters per second.
Yes, because the liquid is relatively stiff, so the pressure wave transfers rapidly from molecule to molecule.
But as the liquid warms up and expands, becoming physically squishier, that acoustic speed plunges.
And when the fluid undergoes the phase shift into a vapor, the acoustic environment changes entirely.
How so?
In the vapor state, the gas is highly compressible. The bulk modulus is very low. Consequently, the speed of sound drops to a sluggish crawl, often hovering around 150 meters per second.
Wow, from over 1,000 down to 150.
Furthermore, the data shows that in the vapor state, this low speed of sound is stubbornly stable.
Stubbornly stable.
Yeah, you can add a significant amount of heat to the vapor, and the speed of sound barely twitches compared to the massive swings you see in the liquid phase.
Okay, but why does this sluggish acoustic speed in the vapor matter so much to a designer? It ties directly back to our earlier discussion on acoustics and flow separation, right?
It does. It is the absolute limiting factor for flow velocity. You have to remember, the speed of sound is the speed at which pressure information travels through a fluid.
Right.
If a compressor is pushing a vapor refrigerant through a narrow restriction, like an expansion valve, the flow accelerates. Because the speed of sound in the vapor is so low, only 150 meters per second, the accelerating gas can very easily hit Mach 1 as it squeezes through the orifice.
And when a fluid hits Mach 1 inside a pipe, you achieve what is called choked flow.
Precisely. Choked flow. Once the flow hits the speed of sound at the restriction, it is physically impossible for it to flow any faster, no matter how much pressure the compressor applies upstream.
Why not?
Because the pressure wave literally cannot travel backward against a flow moving at the speed of sound. The fluid creates a thermodynamic traffic jam.
And a thermodynamic traffic jam isn't just inefficient, it is violently destructive.
Well, incredibly destructive.
The choked flow creates severe shock waves downstream of the valve. Those shock waves cause massive acoustic vibrations, which couples with the structural pipes.
Leading directly back to the destructive resonance and metal fatigue we discussed in the heat exchanger arrays. The valve will literally hammer itself to pieces.
So if an engineer does not know the exact temperature, phase, and corresponding speed of sound of their specific refrigerant, they have absolutely no idea when their system will choke.
They are flying completely blind. And to make matters even more complex, the distinction between liquid and vapor eventually completely disappears if you push the fluid hard enough.
Wait, really? Disappears entirely?
Yes. The sources track a property called surface tension, denoted by the Greek letter sigma. Surface tension is what creates a meniscus.
Like the little curve at the edge of a glass of water.
Exactly. It is the physical boundary layer that separates the liquid pool at the bottom of a tank from the vapor gas floating above it.
Okay, so what happens as you heat it?
As you heat a fluid inside a sealed, pressurized container, the liquid expands and becomes less dense, while the vapor above it becomes more pressurized and denser. The surface tension, sigma, between them progressively drops.
Because they're becoming more similar to each other.
Exactly. And eventually, the fluid reaches its critical point.
And the critical point, the surface tension hits absolute zero.
The boundary completely vanishes. The liquid and the gas merge into a supercritical fluid.
A supercritical fluid. That sounds like science fiction.
It kind of does, but it's very real. It is an indistinguishable, opaque blur that possesses the heavy density of a liquid but the expansive compressibility of a gas. The rules of physics for supercritical fluids require entirely different engineering equations.
So an engineer designing a high-pressure system isn't just dealing with a simple liquid or a simple gas.
Not at all.
They're dealing with a thermodynamic chameleon. As the operating temperature shifts, this fluid fundamentally alters its speed of sound, its capacity to absorb heat, and completely reverses its rules of internal friction.
Which brings us to a final overarching paradigm shift for the listener to take away from this entire deep dive today.
Okay, let's bring it all together.
We began by looking at added mass, the reality that a solid structure's physical identity, its very mass and inertia, is instantly altered depending on the fluid enveloping it.
Right, the car in the atmosphere versus the submarine in the ocean. We saw how changing a shape from a smooth cylinder to a sharp square magnifies that virtual mass.
And how the D'Alembert paradox taught us to separate acceleration forces from constant velocity drag.
We explored how proximity to other structures creates a network of invisible mechanical springs, locking independent pipes into a single, coupled, violently vibrating system.
We discussed how to anchor against those forces using the massive density of tungsten, rather than the thermal sponge of lithium.
And finally, we saw how the fluids themselves are entirely unstable entities, flipping their own physical rules, changing viscosity behaviors, and creating destructive shock waves when shifting from liquid to vapor.
Therefore, a true engineering design is never just a static object sitting on a two-dimensional blueprint. It is an active, dynamic ecosystem.
An ecosystem, I love that.
The empty space around your parts, the invisible fluid rushing through the annular gaps, the ambient temperature, these are not just passive environmental conditions. They are active, physical components of your machine, exerting forces just as real as the bolts, the welds, and the steel.
So if you only design the metal and ignore the fluid,
You are ignoring half of your machine, and the fluid will inevitably tear the metal apart.
that is profound. To bring this all the way back to the beginning, that concrete, predictable blueprint we expect in mechanical design isn't necessarily wrong. We just needed to learn how to look at the negative space on the paper. The fluid isn't just getting in the way. The fluid is the mechanism. If you haven't already, give us a like and follow, and please leave us a comment if you enjoy the podcast. We love to hear from the folks who make this possible.